find very interesting. You're going to learn out how these real FPGAs really work. So we're going to talk about digital circuit implementations, and that's like how do we actually physically build these digital circuits that we've been designing. And there's kind of four ways to do it. There's what are called standard logic, programmable devices, ASICs, and full custom. That's the four categories. So let's start from the left. Standard logic. Standard logic is parts that you buy. They're already configured. They do some function like an AND or an OR or XOR or a latch or a flip flop or a counter. It's a physical part that you buy from some company. And there's usually, in the old days, they had TTL logic, which was bipolar logic. There was 74 series. Then they came out with CMOS version, the 4000 series. The XX is like the part number that has a certain function. These have been around forever. They started in 1963 and TTL and CMOS in 1968. But we don't use them very much anymore because turns out in an ASIC or FPGA, we can put literally thousands of these standard parts and we don't have to kind of worry about putting them on board. So in the old days, what people used to do was, you would have a circuit board and you would have like literally hundreds of these little standard chips on your board. This was the board. And, this might be an AND gate or a bunch of AND gates. This might be some flip flops, whatever. And you would wire them together with wires, either on the board or wire wrap wires and connect them. You've probably done this in the lab. But on a board, there would be literally hundreds of these things. Well, all of those things today can be put into one chip, an FPGA or an ASIC. So the whole thing is replaced by this one chip that sucks in all this thing. So we tend not to use these anymore. You might use them in a very special case if you have one little thing that you needed that was super high speed or maybe super low power that you couldn't do in a FPGA or an ASIC, but that's the only time we use them now. So that's standard logic. Then there was what were called programmable devices, and I put them in these categories. There was originally very simple programmable logic devices, and we'll see what they are in a minute, which came about around 1975. That's a long time ago. And then people kind of combined those to make what were called complex PLDs, which were like groups of these. Again, they're trying to put more chips in one package or more circuitry in one package. They came around 1980. And then today, what you're using in the lab are called field programmable gate arrays. So they're very functional, very programmable. These other ones tend to not to be programmable so much. So these are very programmable. You can reconfigure them, do all kinds of things, and you can put massive amounts of logic and sequential circuitry in them. And they started in 1984, so they've been around for a long time as well. And they just increasingly got more and more complex and more functionality. Then you have ASICs. So unlike these are parts. You buy these parts from a company and then you program them. So like on our boards in the lab, these FPGAs come from Xilinx. Xilinx sells them to this DigiKey, and DigiKey put them on their boards, and DigiKey sells us the boards. But they're parts that are already pre-built. You don't design the parts. You just design how they program inside. In an ASIC, you actually design the chip. You design not only the circuit, the digital circuits, but how the wires go, and you make everything custom for your specific use. These are general purpose in a sense. These are custom. They only do your functionality. And there's two kinds of ASICs. Oh, and as a result, they tend to have lower power consumption, higher performance, and lower cost in per part. I'm going to talk about what that means, what lower cost means. But generally, if you bought a part here, you make it, this could be $1 if you sold high volume. These things can be tens to hundreds to thousands of dollars.
For ASICs, do you also make the components?
You don't do it yourself, but you send it to a company and they build the ASIC for you. You actually, it's a two-step process. You send off the design files to a foundry that builds the silicon, and then that chip that comes out of it gets sent to a packaging house, which puts it in a package, and then they send it back to you. And then I guess you actually send it to a house that has a board and you get it mounted on a board. So there's 3 steps to it. Anyway, these ASICs, and by the way, we can use the same circuitry, Verilog, to design FPGAs, or we can use Verilog to design ASICs. It's the same Verilog. These ASICs, there's kind of two categories. There's what are called gate arrays. We'll see what they are in a minute, but they started around 1981, so they've been around a long time. And then there's what's called standard cell ASICs, which is the more common one that we use today. And they started around 1985. So these things have been around for a long time. Again, the ASICs have been getting more and more complex. Back in 1985, they probably used something like 10 nanometer or 10 micrometer or something like that. Today we're at, 7 nanometers. So these things over the last 40 years, these things have shrunk down like orders of magnitude. Yeah, and the last category is what's called full custom. In a full custom design, you don't use these existing cells that are like these standard cells are like, oh, there's an AND gate. Somebody's done the layout, they've done it. You just use the cell, or somebody's done a flip flop or whatever. In full custom, you do all the layout. You specify where the gates are, where the drains, the sources, all the widths, the lengths, everything. You do it all custom. And the advantage of that, it's even higher performance than ASIC because you can tailor everything specifically for whatever delays you want. You don't use off the shelf stuff. This is only used in very specific cases right now, like for RAMs, because you're trying to pack in as much RAM as you can on a chip, people will do it. Some parts of microprocessors will do custom. People do it for analog all the time, but for digital stuff, it's only used in a small number of cases. Most of the time we're using these off-the-shelf parts that somebody's designed for us. So those are the four categories, and the ones that we're most interested in is this FPGA. We're going to talk a lot about that. And we'll talk a little bit about these ASICs, and we'll just sort of pass over the other ones pretty quickly. Any questions about that? Okay. This is just showing you what a full custom design is. This is the only slide I have on it. In a full custom, this is a circuit we're building, and these orange part here, that's the polysilicon, that's the gates. The green is an NMOS transistor. That's the device well for the NMOS. So the overlap of the green and the orange actually forms a transistor. And this sort of white is the PMOS transistor. Little white squares are connections between different layers. And the blue is the metal connections. But anyway, when you do full custom, you're actually specifying all these layers and what the sizes are and everything. And you use a layout tool, it's called. We're not going to do that at all in this class, but I just want you to be aware that that exists. And that's what people do to make really sort of high volume custom designs. Very labor intensive, expensive, long time to market. So it's only used for special things like memories and special parts of microprocessors. Okay, so next we're going to talk about cell. Oh, did I skip a slide? No, I guess I didn't. Next thing we're going to talk about, so that was this full custom layout. Now we're going to talk about these standard cells for ASICs. This part here. So this is a very, very popular way to do ASICs. So we have a chip, this blue square, big blue square represents the chip. And on the chip, we're going to put cells that have already been designed. So for instance, somebody designed a cell here, like maybe this was a 2-input NAND gate or whatever it was. It's already been built. Somebody's already done this custom layout for us. Now what we do is on our chip, we just place that cell. And we'll place all these different cells. So they've already been built. We just place them on our chip and we wire them together. So the only thing that we do special is we wire them together. And we don't do this manually. We use a place and route tool. And you've been doing this in the FPGA. It's not physical wires. You use connections. We'll see how that works. But in ASIC, physically the wires are placed to make these connections. And commonly these cells are put in rows. So we have rows of cells and then we wire them together. We can also have special blocks, custom blocks, like a multiplier or a RAM or an ALU or something that can also be added. So it has a lot of flexibility. And I show this as some height and some routing channel, but today, this is a little bit old school. Today, we have so many routing layers, like a modern chip probably has more than 10 routing layers. So what happens is the channels become they kind of disappear because we have basically what we do is we have rows of cells that just butt up against each other like that. There's no channel in between them. And then we just route over top of them because there's so many layers to route. So it kind of looks like that. So you can think about this. This routing channel is shrunk down to basically 0 today, or whatever the minimum spacing is for the cells. Yeah, so it's popular approach. Cells are custom designed and they're verified once, and then we just use the cells that have been verified. This reduces the implementation effort, so we're using existing cells. Some libraries provide large capabilities. Yeah, you can have all kinds of things: muxes, inverters, NORs, counters, adders, encoders. I don't know, there's all kinds of wide variety of cells. And sometimes we even buy these from different companies. It's called IP, right? Intellectual property. Somebody will have a RAM or an ALU that we want to use, or whatever, digital cells, and we put them in there. So that's standard cell. Now, the one thing to note about this, when it's ASIC, since we have the flexibility to put these cells wherever we want, like we could put, this could be a mux, and this could be a flip-flop, or, we can move them around whatever we want. But when we build this chip, we're using all the layers. Even though the main thing that we're designing is the routing between them, since we can move them anywhere on the chip is a custom chip with all layers, okay? So when we go to build this ASIC, we have to get it fabricated with all the layers being special for our chip. And so that means more masks, like a full set of masks, and the full cost of a set of masks, which is a lot of money. Okay, so that's standard cell. So the other type of ASIC is what are called gate arrays. And they're usually called mask gate arrays because they're not programmable. It uses a mask or one of the layers in our chip to program them effectively. So the idea here, it's kind of like standard cells. You have these rows of circuitry, and then you have rows of channels that route in between them. But unlike an ASIC where you can move the cells wherever you want, these rows look something like this, okay? We have the blue overlap of the blue and the red is a PMOS transistor, and the overlap of the yellow and the red is an NMOS transistor, and the black are contacts. So these are predefined. These are laid out. The ASIC is designed. All these poly and the contacts and the P and N transistors is predefined. And what you do to make the chip, your special chip, to do what you want to do is you only add routing layers. So since all the lower layers are already predefined and you're only doing the router layers, you only need masks for the routing layers. And this chip can be used by many different companies to just do different routing layers. So it greatly reduces the cost of the mask and greatly reduces the cost of getting a small number of chips, okay? And so, for example, this circuit right here, it's unprogrammed. And then to program it into some function, I have to add some metal layers. So here I've added some metal layers. There's a metal contact right here to VDD. There's a metal contact here that connects a bunch of nodes here. You can see them like that. And there's a metal contact here. And there's a special metal contact here. Well, those few little metals that we've added at the top, routing layers, they make this into a circuit, okay? What circuit would this be? Well, if you look at the top here, these are the P's. We have VDD, and then this is a transistor here, a transistor here, a transistor here, a transistor here. So effectively, that looks like 3 transistors in series connected to this point. And so if I were to draw a picture of that, it looks like P, 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 P. And that's VDD, and this is called out. That's what these 4 transistors on the top. On the bottom, you'll notice I have 2 ground connections. See, this is the ground wire metal, and I've connected here, and I've connected here. And then I have like 2 connections on this side. This is like 2 transistors in parallel. They have connected on this side together, and they're connected on this side. And likewise, these 2 are also in parallel. They're connected on this side to ground, and this side to this output node. So that looks like, if you were to, it's like 4 transistors in parallel. And they're NMOS. One side is ground, and the other side is connected to this out. So what do we get? This is a 4 input NOR gate, right? That's our basic CMOS NOR. So by just adding a few metal layers, a few metal connections here, 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 and here, I made this generic cell structure into a NOR gate. And we do the same thing for all the other cells. We can make NANDs and muxes. We're just adding metal layers to make it into a certain function. And that's called a mask gate array. We basically form the circuit by using the mask for the metal layers, as opposed to field programmable gate arrays where we don't use just a mask, we can program with some other means, which we'll talk about. Okay, so now we've talked about the custom design, we talked about the standard cells, and we talked about the gate arrays. I'm not going to talk about these standard logic because that's pretty descriptive already. We don't design any of those. So now we're going to talk about programmable devices, which is maybe the more interesting topic. So programmable logic devices, they use different technologies. There's 3 basic technologies people use. They either use SRAMs. SRAM stands for static RAM. I think last day in class we talked about this. So maybe I have a picture back here somewhere. Can I draw an SRAM for you? Back here. Oh. Yeah, remember I did this SRAM last day? So basically you have inverter back to back and you have a little transistor, and if you turn the transistor on, you can force this little latch into one either 0, 1 or 1, 0, and then if you close it, you can read it out if you're not forcing it. So that's an SRAM cell. It's got like 5 transistors, and it's just basically a simple latch is an SRAM, but in the SRAM, it's built so that you minimize the area of the cell, and you multiplex them so you can read out different nodes, different cells on one cell. Like normally there's a whole bunch of these connected together, right? So you just read them out on one pin. But that's an SRAM cell. And one thing to note about this SRAM is that, yeah, as long as the power is applied to these inverters, this will remember what it is. But the minute you remove the power supply, it loses its memory. So we call that volatile. So volatile is different than dynamic. Means that you always have to be updating. Volatile means like if there's no power, it loses its memory. But as long as there's power, it will remember it indefinitely. Okay. So this is SRAM, and this is the technology that you guys have been using in the lab. The Xilinx FPGAs that you're using, they're using SRAMs. Some things about this, it's state of the art, so you can, 5 nanometer, 7 nanometer, whatever the latest technology is, there'll be SRAM cells in that technology. Is it reprogrammable? Yes. Is it fast to program? Yes. Is it volatile? Yes. That's not a good thing. We don't really want that, but yeah, it is volatile. Because it's volatile, when we start it up, we have to configure it. And that's what you guys have been doing in the lab. You basically create a circuit, and then you download a bit file into it. What the bit file is doing is programming these little SRAMs to do certain functions, okay? Good for prototyping? Yeah, very good, because you can change it on the fly. You can download a circuit. Oh, I don't like that circuit. Or reprogram with different features, and then it does something different. Instant on, no, because you have to, it doesn't, when you power it up, you have to download the program into it. Security, acceptable, we'll talk about that. Size, these are large. Remember last day we said, somebody asked me this. Where was it? Yeah, I said a DRAM, this is a DRAM, it just uses a transistor instead of these 5 transistors or 4 transistors. So it's much smaller, it's like a quarter. So SRAMs are relatively big compared to DRAMs. And likewise, in the configurable logic domain, it turns out these SRAM cells are big, 6. Well, it can be either 5 or 6 transistors. There's kind of 2 variants. I should have pointed that out. You can have it like this, or you can have a complementary one on here if you want to send these out differentially. So sometimes they'll do it with 5, sometimes they'll do it with 6. These are connected together. Yeah. In real SRAMs, you usually have 6, but like in FPGAs, often they just use 5. So it's large. Power consumption is medium to high. We'll see why that is later on. Is it radiation hard? No. If you get a lot of radiation, it can destroy. These cells are, the memory. You can, if you hit it with radiation, like in space or something, they can flip the value of the SRAM cell. But yeah. Okay, the other types are anti-fuse. Anti-fuse was used way back when. It's not so common anymore. The idea with an anti-fuse is, draw a picture of this. You have a transistor that you want to act as a switch, and if you put enough current through this, a very large current through this, you can force the transistor to become connected. So think about it. Let's say this is an NMOS transistor and this is turned off, okay? So normally we have our transistor here. This is tied to ground. So this is open, right? But also remember that this is filled with metal, okay? There's a this is metal that connects on one side, and likewise, there's metal that connects on the other side. If you put enough current through here, you can actually kind of heat this whole thing up, and the metal will penetrate underneath here, and it'll make a connection. So initially, you can think about it, it's kind of like a fuse. Draw a fuse like, let me draw a fuse symbol, something like that. That's like a, I can't remember, what's the fuse symbol? I don't know. Anyway, normally it's a switch that's open. If you put enough current through it, you can force it to close. And the thing about this is once it's closed, this metal actually physically penetrates under here. It stays closed all the time. So it's the opposite of a fuse. A fuse, you blow it and it's open. An anti-fuse, you blow it and it's closed, okay? It's usually older technology. The newest technologies don't do that. It's not reprogrammable. Once you program it, that's done. It's fixed. It's not volatile. Once you blow it, it's blown for good and it stays shorted. And so you can power it up and it's already ready to go. Doesn't require a config file. It's not that great for prototyping because once you blow it, the chip's programmed, you can't reprogram it. So you got to get a new chip if you made a mistake. It's on instantly. It's very good for security. It's hard to read out. Like one of the things about these SRAMs, if you're smart enough, you can read out what the memory values are inside, so you could kind of figure out what it's doing. Somebody could kind of copy your IP. This, it's hard to read out because it's something buried deep inside the chip. Very small. The fuses are just one transistor. Power consumption is low, and it's radiation hard because you can hit it with radiation as much as you want, and it won't change that metal connection. Okay, that's the anti-fuse. Older technology, not so popular today. So the other one is EEPROM, E-squared PROM, or flash. And we need to explain that. So these are the two types that are used more commonly today, either SRAMs or E-squared PROM. So we need a little lesson here, which some of you may know or not. So E-squared, okay. So ROM means, anybody know what that means? Anybody know?
Read-only memory.
Yeah, ROM means read-only memory. So it's a memory, like if you buy from a factory and they program the memory to do something, you can read it. That's read-only memory. So that was the first type of memory that they had. It's read-only, not like RAM where you can read and write it. And then they had PROM, which was programmable read-only memory, right? And so those were like, like the anti-fuse could be a programmable ROM. You have a ROM, you blow the fuses or the anti-fuses, and it has a certain memory that it's got it. So it's a PROM. And then they came up with what were called EEPROMs. And EEPROMs were electrically erasable programmable read-only memory. And the way they worked was you had if this was your chip, you may have never seen these now. They're not very common anymore. Here's your chip. There used to be like a little glass window on the top of the chip that you could see through. So that was window. And what you did was you could program it like a regular program read-only memory. But if you wanted to erase it, you put it in a tray, you put your chip in it, and you had a ultraviolet light. So, like a tanning bed, only ultraviolet. So this was UV light. And when you put UV light, it went through the window and it wiped it all out. It erased the memory inside of it, okay? So that was called an EEPROM. And then they came up with EEPROM, which is electrically erasable programmable read-only memory, or sometimes you just call it E-squared PROM. okay? And the way it works, the most common technology is you have a transistor and you have a gate on it, and then you put another gate on top of that. It's kind of like a dual gate, okay? And what happens is if you put enough, and this is a very thin layer here, thin silicon dioxide, SiO2, right? So it's like the gate under here, but it's a thin layer. And if you put enough voltage between these, what you can do is you can force charge through here, and the charge will store on this gate. And then even once you remove this, the charge is stuck in between there. And by the way, it's a quantum mechanical effect. Put enough voltage, the charge will jump this very thin layer and stick on this gate. And once you remove it, it's still stuck on the gate. Okay. And so now this gate is either open. If there's no charge there, it's open. But if the charge is there, it closes the transistor. So that's an E-square prom. And then people made special versions of it that had sort of banks and stuff. And effectively, E-squared is the same as flash, is probably the more common term, like flash memory, like in your USB drive or a memory card, or even today, the hard drives are being replaced by magnetic hard drives with flash memory, okay? And they all are based on this idea of this storing charge on this dual gate transistor. Now, so what are the things about this? What are the highlights? It's usually not quite as advanced. SRAM, you can do it with state of the art. EEPROM flash, like this is a sort of a special, not every this is only special for a flash. Like most circuits don't need a dual gate like this because it's extra layers and special processing. So it's usually a few generations behind. So it's not as dense. It's reprogrammable. Yes, you can. Oh, by the way, yeah. Back up here. If you put the charge the other way, like this, then you can make this charge jump back up. So you can reprogram. You can make it a 0, 1, electrically program it one way or another. So yeah, it's programmable. It's usually slower than SRAM, like programming it one way or another. Putting that charge through the transistors, through the gates, the dual gates, is slower than just turning a transistor on. Is it volatile? No. Once you put that charge in there, it remembers it even after you remove the power, so that's nice. It doesn't require external config file. Good for prototyping, yes, because you can still program it or reprogram it. Instant on, yes, because it remembers where it was at. Security is very good because you can't figure out where the charge is on in these internal gates. Medium size. It's a dual gate. It's not as big as an SRAM, which has 4 transistors or 6 transistors, but the dual gate is bigger than just say 1 transistor by itself. Power consumption is medium, and it's not really radiation hard because, if you get radiation coming in here, it can add charge or discharge this little node because it's a pretty small little node with only a small amount of charge. Okay, so that's the technology. So we're mainly going to focus on SRAM because that's what we're using in the lab, but those are the different ones that exist. Any questions about that?
Yeah, I'm working with the EEPROM of the Arduino board, and when I was doing research on it, it says that it can only do, I forget what it was, but something on the order of like 50,000 read-write cycles.
Yes. Yes. So that's because this charge, like when you apply this large voltage back and forth, eventually it degrades this oxide layer and these transistors. So they have a maximum cycle time. And also, if you notice this, like if you ever if you get a laptop and you're using what do they call it? A semiconductor memory instead of a hard disk, then they'll say, often you want to use it for things, it'll have a read-write cycle time, maximum number of read-write cycles as well. So it's often called, like originally people just used it for their programs, right? So like, say you have your laptop. Oh, by the way, flash is used in all your cell phones as well.
Yeah, a lot
Um,
for Macs that use like integrated SSDs, they have like lifetime based on the cycles that you write or read from them.
exactly, because this degrades over time. But originally what people used to do is they'd have a hard drive, which would connect to this external hard drive, or it could be inside there. And the flash they would use for the programs. Because, like say you load a Word or some program, you don't change it. You download it, you only do it once, and then they would use this for all the data. But then
Okay.
they just said, oh, you know what? It turns out, well, they they go for 50,000, 100 cycles. Well, people throw their phone away or throw their laptop away after 2 or 3 years. So most of the time, unless you're doing some crazy reading, writing all the time, it'll outlast the product lifetime anyway. So
Right. Okay. Cool.
yeah.
Thanks.
So
The main issue with that is like Flash is so fast sometimes that it could be used instead of RAM. The problem is the more you write, you degrade the memory. Uh,
yeah, it's slower than RAM too, though. That's the other thing. It's usually slower. Yeah. So if you like in your laptop, this flash and hard drives, those aren't your primary memory. Like those are like secondary memory. On in your chip, you have like say 8 or 16 gig of RAM, right? That's SRAM because it's super fast. So you download this stuff into your SRAM, and then your programs are running on this SRAM, and then every once in a while you're pulling data from either this hard drive or this flash. Okay. Anyway, that's a little off topic, but good to know. Okay, so those are the technologies. So how we doing? Oh yeah, we got some time. So we said there. Oh, yeah, let's back up. So we said there's simple PLDs, complex PLDs, and then FPGAs. This is the one we're most of, but we'll kind of walk through them a little bit here. So the simple PLDs, these were the first ones, the first programmable logic devices. They mostly used anti-fuse technology, and there were kind of three variants. There were what are called PLAs, PROMs or PROMs. We already kind of talked a little bit about those, and PALs. So what's a PLA? A PLA said, oh, okay, we want to make a bunch of ands and ors. Instead of putting and gates and or gates on our circuit, we want to make an array of ands and ors so that we can do any sum of products function, right? So we can build any logic. No sequential circuits, just logic, but we can build a very complex logic. So what these look like, these little AND gates right here basically have a bunch of connections. It's not shown here, but there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12. That's a 12 input AND gate. And I've just put them on one line. And this circle says, oh, there's 1, 2, 3, 4, 5. There's 6 inputs. And then we have the signal and its complement coming out. And these little bubbles say these are our little places where we can program. They can either be opened or closed, whether we program them. So we can make any logic function of the 6 inputs, any ANDing of the 6 inputs or their complements into this one gate. And likewise, there was many of them. So we can have a bunch of different AND functions here. And then the ANDs came out, and we had a fixed array going into these ORs. Yeah. Sorry, no. In this one, the PLA, these were ORs, but we could program any of the ANDs into the OR. So we can have any logic function of any AND and any OR for the PLA. So it was any logic function of ANDs or ORs, okay? This was flexible to implement any sum of products. The PROM had a fixed AND array, so the connections into the ANDs was fixed. The solid dots mean that they fixed. That was already done in the factory, and then you could program the OR array to never whatever of these given ANDs that you had. And the PAL had a programmable AND and a fixed OR. So those were the three types of simple PLDs. They were only used for logic functions, but you could put a lot of logic into them. And these were one-time programmable. Once you programmed them, that was it. It was fixed. Often we would put these on a board and we put it in a socket. So you program it. If you made a mistake, you could pull it out of the socket and put a new one in. Any questions about that? So that was great, but then people said, well, I want to build things like counters and, ALUs and stuff. And I said, well, how about we take our PALs or PLAs or whatever, we have those already, but then we're going to add some extra circuitry, IO blocks and interconnects between these. And they use these little cells with IO blocks that had flip-flops in them. And they had some programmability in the flip-flops, but basically they put a bunch of these together because they could put more circuitry on a chip, and they have programmable logic, and now I can make, or sequential logic, and now I can make more complex digital systems. So those were called complex PLDs, and they even exist today. For instance, Altera, which is now AMD, or no, it's Intel. Intel bought Altera, and AMD bought Xilinx, right? So this is now Intel. They have the Max 7000 family of CPLDs that you can still buy today. The reason that people still use these is that they tend to be really low power. Okay, FPGAs with SRAMs that are bigger and they take more power. If you need a really super low power programmable device, then you kind of still go for these CPLDs. But that was a CPLD.
Professor,
Yep.
what do the I/O blocks consist of? Is it some sort of control FSM for flow, or?
No, this is the IO block right here. Or sorry. No, this is the microcell that the PLAs have kind of be going towards the IO blocks. They have this. The IO block will just be a simple, it'll look something like this. You can have an input or an output and it's programmable.
Okay, thank you.
They connect to a pad like that. And the output is, you can, our tri-state buffer, it'll have a special tri-state buffer for driving a pad. It kind of look like that. Okay. Okay. The next thing we're going to talk about is FPGAs. So this is more interesting. We only have 2 minutes. You know what? I don't think we're going to start talking about FPGAs today because that's a long discussion. Okay. Anybody got any questions before we end? No questions? Oh, somebody said, don't HHDs have read-write cycle limits too, due to the amount of times we can change the magnetic spin on the plate? I don't know. I think HHD, like hard disk drives, they can go for a long time. I don't know what the read-write cycle is, but it's years. There's hard drives that last for 20 years or something. So they might have some limits, but they're not practical limits. Okay, no questions. I guess that's it. So next week we'll continue on with FPGAs. Talk to you later. Bye.